for coming. I really appreciate that extremely kind introduction. Thank you very much. And everybody zooming in, I appreciate you being here as well. So I am Storm Cruz. I'm going to be talking to you a little bit today about some of the work I've been doing for my master's degree here the past couple of years on the spatial ecology of partially migratory Rocky Mountain elk. So just to get things started, animal migration is this kind of movement behavior where animals are seasonally moving between discontiguous ranges. And this phenomenon is abundant in a wide variety of taxa. Almost every major animal taxa has some level of migration in a species somewhere. And there's a range of causes etiologically for this. We tend to focus on improved access to periodic resource abundance, such as vegetation quality or water, but also breeding and spawning behaviors can motivate migration, such as we see in salmon and cetacean migrations mostly. But migration is only one in a continuum of what we call movement strategies, which are essentially broad-scale movement behaviors exhibited over long periods of time. And like I said, it's a continuum. And so on the other end of that continuum, we can see residency. And residency is essentially where individuals are displaying home-ranging behavior for the entirety of the year, so they're not migrating. Partial migration, however, is where you have a singular population that has movement strategy diversity within it. So you might have some individuals who migrate and some individuals who don't. So why would we want to study this? So there is some evidence that interpopulation diversity and movement behavior may actually increase overall population fitness. So it can influence population dynamics. And movement strategy can influence survival and reproductive output of individuals of particular strategies. And we tend to think of this as a series of trade-offs. So as we can see up here, maybe we can imagine if migratory individuals are migrating, they might improve their access to high quality resources, but they're also increasing their access to risk exposure and energetic expenditure. Whereas non-migratory individuals in the same population might not benefit from those high quality resources, but they're also not detrimentally affected by that risk. And there are some open questions about partial migration theoretically. Most of our theories are based on partial migration in birds and fish, but we've been increasingly studying this in ungulates over the past few decades. And so one of these questions is the mechanisms of the maintenance of partial migration and why is partial migration so abundant among populations. Additionally, we want to know the determinants of relative strategy frequencies. Is this due to demographic balancing between strategies or something else? And we'd also like to know how do overwinter ranges support abundances of multiple strategies? Is this due to differentiation of resource requirements with lower interest in competition or some other mechanism? And what I'm talking about today will kind of relate to that last question. So a very good system to study this in are elk or Cervus canadensis. And this is because they have high movement strategy diversity and they tend to have partially migratory populations. So these are one of the largest members of the family Cervidae or the deer family. And ecologically, they're primarily grazers, so they'll kind of graze along native grasslands, but they'll also engage in some browsing behaviors on forest edge habitat. They are highly gregarious, which means they're extremely social. They aggregate in these large collectives that we call herds, like you can see here. So biogeographically speaking, we can see that they're concentrated natively into North America and Central and East Asia. And this lime green color here is kind of a recreation of their historic range. We can compare that to the approximate distribution of this dark color here, where they currently reside. We really want to focus on North America today, and as we can see, they've been extirpated from the vast majority of their habitat east of the Rockies, mostly due to human efforts, unfortunately. But we want to focus in on the Rockies right there today, and specifically the state of Colorado, where we can say there's abundant elk habitat. So other than our interest in partial migration, why should we study elk? Why would we be interested in them? So in the state of Colorado, Rocky Mountain elk are of extremely high economic importance. So as I said, they've been extirpated from most of their range, and this actually includes Colorado. They were almost completely wiped out until about a century ago. Management efforts brought them up to their current numbers, which today is estimated at about 300,000 individuals, which is nearly a quarter of the entire national population estimate. So as far as states go, Colorado has by far the highest number of elk. They're heavily managed for hunting opportunities primarily, but also ecotourism, recreational interests, and wildlife livestock interactions, because they have the ability to carry lots of diseases that can impact cattle, and ranch owners are obviously very concerned about that. And I'd like to underscore that the vast majority of the state's conservation funding comes from selling hunting licenses. So economically speaking, elk are very vital for conservation of wildlife in the state as a whole. But they're also very significant ecologically. So they play roles in predator-prey interactions with lots of the larger predators in the state. We can see a black bear here is feeding on this poor calf, but they're also prey for mountain lions as well as coyotes and soon to be gray wolves. And they exert top-down effects on vegetative and forage structure on the landscapes that they feed upon. So they're ecologically significant in that fashion as well. Lastly, their migratory behaviors basically act as a physical linkage between discontiguous locations, which is influenced by geochemical cycling at large scales. So just to introduce my study area here, so this is the state of Colorado, of course, and I want to draw your attention to these kind of four colored areas throughout the state. This looks like I probably have four populations, but analytically speaking, I actually have five. So up here in the yellow, near Craig, Colorado. In the west, we have the Bears Ears herd, and on the right, we have the Steamboat herd. Arguably, they're subpopulations of the same herd, but for our purposes, they'll be analytically distinct. Near Aspen, Colorado, in the red, we have the Avalanche Creek herd, and the green down here near Montrose is the Uncompahgre herd, and then down here in the blue is the Trinchera herd on the border with New Mexico. So we have five analytical populations of elk we're going to be looking at today. So just to look at that data, I did not capture this data. This was all the doing of Colorado Parks and Wildlife, who very graciously shared this data with us. But we have field seasons between 2017 and 2021. And basically, people went out and they captured these adult female elk on their winter ranges early in the year. This was via helicopter net gunning or chemical immobilization. And very significantly for our purposes today, they fit them with these GPS collars. And that gives us locations and timestamps so that we can study their movement. In the end, I ended up with 387 individuals in my final data set. And notably, each of these herds was actually studied for different periods of time, but it ranged between 2 and 5 years per herd. So just to get a feel for what that data actually looks like. So here are the locations of one residential individual over an entire year. And of course, this is neat. We can see kind of the geographic distribution of where that individual went. But where this becomes analytically significant is when we can use remote sensing products to kind of measure environmental covariates that we can then relate to these locations. And in this way, we can understand much more about their ecology. So getting into my first chapter, we have a number of questions. The first one I want to address is, how do movement strategy frequencies actually differ among populations? And this is to say, what is the ratio of migratory to non-migratory behavior? So why should we estimate this? Well, it's very likely that it varies across populations. And given that strategy influences fitness and risk, relative strategy abundances should play some role in population dynamics. So it should be useful to estimate that variation among populations. So this gets me methodologically into movement strategy classification. So I wanted to categorize each individual elk as being either migratory or non-migratory. And the way that I could do this is with what are called net square displacement methods. So what we have here are just kind of a loose geographic distribution of points. Cool to see, but can't tell us much unless we associate them with timestamps. And once we do that, we have a movement trajectory where we can see the actual order from time 1, 2, 3, or 4 that this individual traveled over time. And what we can do is basically measure what we call displacement. So here in this nice little graph, we have displacement on the y-axis, time on the x. And what displacement is actually the distance between each successive point with respect to the initial location. So you can see we're plotting that over time. And it's all with respect to that initial point. And what this actually looks like and what this can tell us, I'll give you an example. Here is one migratory individual's point distributions over a full year. And if we were to plot its NSD or its net square displacement graph, it looks something like this. And so this is a really characteristic migratory graph. They're not all this pretty, but this one's pretty darn good. And there's a lot of information we can extract from that. So we're able to identify and relate geographically when and where they're in their winter ranges, their summer ranges, and we can even see their particular migrations and when they occur and where they occur. So there's a lot we can extract from these NSD plots. But primarily for our sake, the important thing is this is a migrant. We can identify that it is a migrant. On the flip side, we can look at a residential individual's locations over a full year. And its NSD plot is going to look something more like this. And so this is actually this nice little kind of average flattening out over time with some variability. And this is actually exactly what we would expect if an individual is engaging in home ranging behavior. So there's no migration we can see here. It's just home ranging all year. We put these side by side, it's really easy to tell how distinct these patterns are from each other. So in some instances, it's not that hard to compare a migrant to a non-migrant. But where I'd like to draw your attention here is the scale. So this migratory individual traveled about 120 kilometers between ranges, whereas a resident didn't go any further from 7 kilometers from his initial location. So in this sense, I can kind of formalize the movement strategy classification process. And I use an R package called migrate-R. And this let me fit models to those NSD graphs. And I can estimate strategy and importantly, phenological parameters like departure dates and arrival dates. I could do this at the yearly level per individual. Importantly, I incorporated elevation, but for the sake of this, I won't get into that. But it's for 387 elk, which took a hot minute. And I was able to estimate movement strategy frequencies for each study area. So on the x-axis here, we have each of my study areas, and on the y, we have how many individuals were in my data set from that study area. And where I'd like to draw your attention are these kind of bold numbers up at the top here. And these are actually the frequencies of migratory individuals within that herd. And the takeaway from this is basically that it runs the gamut. There's quite a diversity of gradient of movement strategy ratios. So it goes from about a fifth to about a third to about half, about 3/4 to 100% of individuals within these populations were migratory. So it does seem very diverse as the answer. The next question I want to explore is whether do elk differ in resource selection as a function of their movement strategy. So are migrants and non-migrants responding to the environment in different ways? So why should we study this? We want to identify if and how these strategy responses differ, because if we see differentiation of response, this could help support theories of the maintenance of benefits of partial migration. Also, knowing strategy-specific preferences and resource requirements can make management of those populations. Even if there is no difference, overall resource responses can inform us of the spatial ecology of elk. So I wanted to basically investigate this in a seasonally specific fashion. So I needed to delineate seasonal space use. And I wanted to separate this into basically winter 1, summer, and winter 2, so that I can have winter and summer models, estimates of space use. And for a migratory individual like this, it's actually pretty easy to pick this apart when they're in their winter and their summer ranges. But we can identify this by those phenological parameters, the departure and arrival dates. And so I estimated seasonal space use with this information using 95% kernel density estimates for each individual. And basically what that is just a mathematical model that measures the density and intensity of locations. And this is very easy for a migratory individual, but non-migrants don't really have super obviously clear seasonal space use from an NSV plot. So in order to assign seasonal periods for them, I basically took the median phenological parameters for each migrant in that herd, and then I could seasonally delineate that period for non-migrants. And this is what that looks like. So I have on the left here, seasonal space use KDEs for a residential individual, and each color is representing a seasonal period. Whereas on the right, I have the same thing for a migrant, and you can see it's, in its winter range, migrates, summer, back, winter again. And the reason I want to estimate these is I need measures of availability to study resource use and resource selection. So these are both varieties of resource response. I fit use models, but we're not going to talk about those today for the sake of time. So we actually want to be focusing on selection today. And this is basically disproportionate association of locations with resources in relation to their availability. So again, availability is very important here, and that is the spatial availability, which is that kind of KDE home range estimate. So just to give you a very simplistic idea of what a resource selection function is, which is the mathematical model we would use to study resource selection. Here we have kind of our estimate of space use, which is this blue circle, and then all of these individual locations represent points where an individual was. And then I just, for simplicity, have a singular resource here, which is this patch of forest. And you'll see that these locations are not associated with that resource at all. They appear to be avoiding it, in fact. And this is what we would call negative selection or avoidance for that resource. On the flip side, we have positive selection. And this is basically where, compared to the availability of that resource within the home range estimate, a lot of these points are disproportionately associated with that. So this is strong positive selection. It implies that this individual very much cares about that resource. Just to see what this looks like with actual data, on the left here, I have the raw points, just the XY coordinates for an individual. And in the middle, I have the spatial availability delineation from those kernel density estimates. And on the right, you'll see I have all these red dots. So these are just random points, and we're actually extracting the resource values within that spatial availability. And that way we can quantify the availability of a resource with respect to what is used, which are the actual locations we see there in the black. So I had a number of covariates that I wanted to extract to build these strategy-specific selection models. And just for our purposes, I have 4 covariate categories, basically, that I wanted to investigate if there were differences in. These are anthropogenic, habitat, productivity, which just means vegetation, and then snow. These are basically composed of various covariates that comprise these sort of categories, but we don't have to worry about that today. Suffice it to say, just we're trying to test for these categories. And I'm specifically going to focus on a couple of my anthropogenic and habitat results in the winter model for the sake of time. So just to be more explicit, I fit herd season strategy models at so the summer and winter level per strategy, per population. And I extracted used resources within those range estimates and compared to availability with respect to these random points. I used what's called a generalized linear mix model, which is GLMM, with a binomial response. And that just means the response is 0 or 1. And here that represents 0 is available, 1 is what's used. I had random slopes and random intercepts from my random effects, model selection to AICC, And importantly, I removed collinear covariates for statistical reasons, and that means in a few of the slides you're about to see, there are some missing estimates, and that's why. So before we get into all those, I kind of want to walk you through how to interpret one of these plots. So the covariate we actually have up here is distance to anthropogenic development. We wanted to see how they will respond to that. This is the particular herd we're looking at, avalanche. And then the colors represent migrant and non-migrant, and red and blue respectively. On the y-axis here, we actually have the estimate for strength of selection, essentially. And the bars are very important here. So these are the 95% confidence interval estimates of that parameter estimate. And so this little dashed line here is going to be important for us. Basically, if the confidence intervals are entirely above that line, this is positive selection. If they're entirely below, this is negative selection. If they cross the line, this is a non-significant response. So we're not really detecting any preferential selection in that case. And just to make things a little bit simpler, you're going to see a lot of varieties of response because the trends were kind of inconsistent among study areas. And so I'm going to have kind of a migrant graphic, non-migrant, positive, positive selecting for this. So we also have negative, and NS is not significant. So we can see here, with respect to distance development, we see an overwhelming selection for areas away from human development. So we all seem pretty averse to human development in this case. We do see one example of non-significance here and steamboat non-migrants, but for the most part, we can kind of infer that they are avoiding development overall. With respect to distance to roads, again, they're selecting for areas away from roads. They are averse to this particular resource. And this seems kind of overwhelmingly the case across the board, regardless of movement strategy in every study area. So that's a pretty major takeaway from the study, actually. If we look into some of my habitat covariates, I just kind of want to point out open habitat because this really clearly conveys how environmentally contextual some of these resource responses are. You can see that the trends are not consistent across study areas for the most part. But most importantly, for my purposes right now, I want to point out that there's evidence for different kinds of strategy-specific differentiation there. And what I mean by that is we can be confident that different strategies are responding to the same resource in different ways. I want to highlight one particular kind, which is one strategy response is what I call this. So we can see that migrants are actually selecting positively for open habitat compared to what is available. Non-migrants, we have a non-significant selection. So they don't really seem to have any particular preference. And so there is a difference in the response they're exhibiting here. Another type of differentiation is directional differentiation. And this is where we can see migrants and avalanche are positively selecting for this in a pretty strong manner, while as non-migrants are selecting against it. Lastly, just to highlight another form of differentiation, I looked at distance to water. And I know it looks really close, but believe me, there is a selection strength here. These confidence intervals are not overlapping. And so because of that, we can be confident that non-migrants are responding more strongly to this resources compared to migrants. And then in avalanche, we have another example of a one strategy response. So kind of one of the takeaways here are there are multiple varieties of response differentiation that we can see in a strategy specific fashion. So we can have no difference, which looks like this. Selection strength, which is going to look like that. One strategy responses, like that. And then directional differentiation. But another primary takeaway is that this is highly environmentally contextual and seems to be very inconsistent across study areas. But I think the important thing is that we've been able to identify that there are or is some evidence for differentiation. So getting into my second chapter, I'm specifically looking at migration in this chapter, so no longer partial migration necessarily. And I have a few questions. I'm looking at the drivers of spring migration phenology, and phenology is just a fancy word for biological timing of some phenomenon. The first question I want to ask is, how do the timing duration of spring migrations relate to peak cleanup in differing periods of their journey? So before we get into that, why should we study phenology? So if we understand how migratory phenology relates to resource dynamics, this can inform us of the drivers or maybe the origins of migratory behavior. And the actual way that they relate to this, basically the way migratory phenology relates to vegetative phenology, seems to be somewhat conflicting among different ungulate species. So different species show different responses, the same species in different systems sometimes have different responses, and this includes elk. We also want to study this because climate change is very likely to change the spatiotemporal aspects of resource distributions. And if that influences the timing of migrations, that's definitely a relationship we want to understand. So before we get into that, I want to give a little bit of theories to sort of motivate this chapter. So the forage maturation hypothesis is basically this idea that ungulate migration in the spring is primarily motivated by preferential selection for high quality forage. And this relates to something that we call the green wave. The green wave is this idea that spring green up of vegetation is going to sweep across the landscape like a wave in time and space. And we assume that individuals are going to be responding to this, like we see this individual here. Colloquially, this is called surfing the green wave. And basically it means that they are timing the movement response that they exhibit in order to maximize access to the peak of that wave as it moves across the landscape. So as it moves with it. However, basically the spectrum of possible responses to green wave phenology is larger than just the concept of surfing. We have a variety of possible responses. So to give some examples here, I'm sorry, you can't maybe read that at the top, but basically what we have here is an image of the wave of green up over time across the landscape. If we look at the top at exhibit A, this is a pretty good example of surfing. We can see if these arrows represent an animal, it is basically moving in concert with the peak of this wave as it sweeps. But on the flip side, we can see in exhibit C, this is what we call jumping the green wave. And basically this individual is not moving to try to match the peak as it moves across the landscape. It is actually kind of skipping ahead specifically so that it can come just in time for peak forage quality at the summer range. So it doesn't care much about what the forage quality it encounters along the migration is. It just wants to arrive on time to hit that. And again, this is prioritizing peak forage at different periods is basically what this is illustrating. There are different responses to green wave phenology. And some pretty classical examples of each are wildebeest are very classical surfers, and Scandinavian red deer have been illustrated to engage in jumping. And so we can kind of think about this in sort of a three-period fashion if we want to study this. And I'm going to give some, so basically, sorry, we have the pre-departure period, which is immediately prior to the migration itself, and the post-arrival, which is immediately after arrival. And we can think of this as a series of trade-offs, and I'm going to give some kind of extreme examples of different ways that they could behave to this. And so something we have to keep in mind is that the timing of migration is the thing that's facilitating forage access for animals during each period. So we could think of basically this idea of lagging, and this is where they're prioritizing forage access in the pre-departure period. And basically what they're doing is delaying their departure date and essentially misting the green wave along the corridor, but in the trade-off, they're increasing their forage access during the pre-departure period. You could also have surfing, like I just explained, where you're prioritizing that forage access along the migration. And lastly, you have jumping again, where you're prioritizing forage access upon arrival at the summer range. And so these are kind of the most extreme examples where you're trading off optimization for one period at the expense of the other two in all cases. But in reality, it is some combination of these almost certainly to varying degrees. And the degree to which you're optimizing which ones in what ways basically constructs that trade-off. So again, the access to quality forage is facilitated by the timing of movement. So we explicitly want to relate migratory phenology to green wave phenology. We want to ask, how does peak green up actually influence the timing of movements in elk? Which periods or regions are elk prioritizing or responding to? Is it jumping, surfing, lagging, or some combination of these? It's determining migratory timing. So in order to estimate this, I needed to get migratory phenological parameter estimates, which is just a very fancy way of saying departure and arrival dates. And like I said earlier, I have these, these were estimated from the classification outputs from my migrate R models and the NSD plots. And I'm specifically focusing on spring migration if I haven't made that clear yet. So once I got these departure dates and arrival dates, I could calculate duration, which is just subtracting the two from each other. And in this chapter, I'm explicitly looking at three herds, which are avalanche, bear's ears, and incompagre. And the reason for this is that Trinchera and Steamboat, the character of their migrations was very different in those herds, and they would have been outliers in these models compared to the others. And so my total sample size for this was 131 individuals. So if we want to relate this to forage quality, how exactly do we measure that? So I need to introduce the concept of NDVI and also IRG. So NDVI is the normalized difference vegetation index. This is a remote sensing product. You can calculate it from satellite imagery. And this is effectively a measure of forage quantity on the landscape. And that's going to be this dark green curve here. And basically what we can see here is spring green up occurring when this kind of peaks up there and then it levels off. And then with fall senescence, it dies away. And that's just the pattern of forage quantity with the seasons. But we're more interested in is forage quality, given the forage maturation hypothesis. That's what we anticipate they're responding to. And so IRG is what we want to be looking at. And this is the instantaneous rate of green up. It is literally the derivative of the NDVI curve. So where the rate of change is highest on the NDVI curve, that's where the peak of IRG is going to be. And that's what we assume they're trying to optimize. So this is a measure of forage quality. So I calculated that derivative in a daily perspective for IRG estimates at the pixel level for the whole state of Colorado. So I could use a Yeah, so I wanted to use this to relate forage quality to migratory phenology explicitly. So what we have here is a raster, which is just a spatial representation of the covariate. And what this is on the y-axis from this kind of like orange to green color is the actual day of the year where peak forage quality occurred at each location. So it's spatially explicit peak forage quality. And what's very interesting about this figure is you can actually kind of see the green wave a little bit. You can sort of visualize it as it's sort of moving across the landscape with increasingly delayed green up. So this gave me a measure of spatially explicit timing for peak forage quality that I could relate to migratory phenology. In order to basically relate this to those 3 individual periods, pre-departure, during, and post, like I had mentioned, I needed to estimate space use for those periods. So I used occurrence distributions, which is just a cribbing method from CTMM that we can get from the locations during each of these periods. And I did it 2 weeks prior, 2 weeks following, and during the migration. So within the occurrence distribution boundaries, I extracted the average dates of peak IRG, remember forage quality, for the year for all pixels within them. And I also looked at variation in that date along the migratory corridor itself. By the way, if I ever say corridor, that's interchangeable with migration. And I wanted to build 2 models to see how this influenced different phenological parameters in migration. And these are departure date and duration as my response variables. Again, I used GLMMs, generalized linear mixed models, with herd as a random intercept. I tried to fit random slopes, didn't converge, unfortunately, but and I engaged in model selection via AICC. And so these are my covariates again, just a mean peak date before, during, and after the migration, and then the variation of peak date along the migration. Additionally, I wanted to look at distance as a covariate, and this is just the distance between the summer and the winter ranges themselves. But before we get into the results of that model, I actually want to show you some maps so we can kind of contextualize the nature of these migrations and how it varies among study areas. I do want to apologize for the color scheme here. I tried to make it work, but everyone I showed it to was like, I'm a little confused. But basically, each contiguous line is one individual's spring migration. So that's what we're looking at here. And I'm going to zoom in on each of these individually, but just to give you a feel for the individual sample sizes. At Avalanche, you're looking at 40 individuals. Bears Ears is 62, Uncompahgre is 29. So at Avalanche Creek, I apologize, it's a little blurrier on this big projector than I was hoping, but this area is extremely heterogeneous topographically. So there are lots of mountain peaks, there's a tremendous elevational gradient. And basically individuals here, they show a lot of corridor diversity. So they're not all moving along the same corridors as we can see. But what's happening in this herd for the most part is they're showing short range, high elevation migrations. So if we look at the scale bar here, that's about 25 kilometers. Individuals here average on about 30 kilometers for a migratory distance, but the elevational gradient can be up to 1,000 meters in elevation change. So they're going very high from lower areas. With respect to Bears Ears, we can see there's kind of this really nice population level corridor that they're showing. They're actually moving from west to east here to this kind of more mountainous, greener region for when they arrive in the summer. If we look at the scale bar here at 60 kilometers, these are actually traveling much, much farther than the Avalanche Creek curve. I think on average, they go about 80 kilometers. I think we had one that goes 140, which if I'm not mistaken is pretty unusual for Colorado. That's more of like a Yellowstone size distance. In Uncompahgre, it's actually pretty intermediate between the other 2 herds. There's a good bit of little root diversity here, like we have this one individual who God knows what they're doing. But this is basically moderate distance, high elevational migrations that are shown in this herd. That's sort of intermediate distances compared to the other 2. If we want to more kind of quantitatively make this explicit, here on the x-axis, we have our study areas. And here on the y-axis is the day of year to look at the spring departure dates. And we can see that Bears Ears and Uncompahgre on average leave around the same time. It's about a little over 3 months into the year, whereas Avalanche is leaving quite a bit later than the others. We do have these crazy outliers in Uncompahgre. I don't know why these 2 left in July, which is very interesting, but this kind of shows you the variability we can see here. If we look at migration distances, on the y-axis here, we have distance in kilometers. And we can see there's a really stark difference that we could see from those plots. Avalanche is kind of going no more than 30 kilometers, but on average, just about 20. Bears Ears is on average about 80 with a lot of variation in there, whereas Uncompahgre is intermediate again, around 35 on average. And the migration durations actually, with durations in days on the y-axis, the pattern we see is actually pretty similar to the pattern we see in distances. But there's a ton of variation there, with Bears Ears usually taking about a month and the other 2, 20 days or less. So yeah, the takeaway is there's lots of variations both among populations, but also within populations. So just looking at the actual outputs of my model, the most important covariate is what I'm explaining here. If you care about the other covariates, we can talk about at the end. But basically, each color here for the departure date model is representing an individual herd. So avalanche is in black, Bears Ears is in red, and Ucapagre is in green. And this sort of trend line here is the global trend of the full model. So on the x-axis here, we have the date of peak greenup along the corridor itself. On the y-axis, we have the spring departure date. And what we're seeing here is a very strong association. And kind of the layman's interpretation of this is the later that peak greenup occurs along the corridor, the later they decide to leave, the later their departure date. And so this is actually pretty good evidence for surfing. This is quite a strong association. For my duration models, I had two pretty important covariates. And the first one you would never believe, which is that duration is a function of distance. The farther they have to go, the longer it takes them, which is a pretty intuitive result, but it is very interesting to see the variability there. The more important result here, though, I think, is duration against the date of peak greenup post-arrival. So basically, if their summer range greens up at a later date, they are taking longer to get there. And this kind of suggests that there's some sort of modulation of the duration so that they're reducing phenological mismatch. And what I mean by that is they are trying to minimize the amount of time between when they arrive and when peak greenup is occurring at that particular area. So takeaways from these models are the departure date is delayed when peak greenup occurs later on the corridor, which is kind of like surfing, and duration is prolonged when peak greenup occurs later at the summer range. And so if we take this together, this is kind of evidence for these trade-offs in two different phenological migratory parameters, departure and duration, in response to peak forage access during migration and upon arrival. So the second thing we might be looking at here is how optimally do migrants time their movements and how much variation is present among individuals. So why should we study optimality heterogeneity? So optimal foraging theory is this idea that animals should move in order to maximize their access to resources. But organisms kind of by virtue of necessity have to engage in trade-offs. They can't maximize access to every single resource simultaneously because they're influenced by so many factors. So they have to choose. However, suboptimal prioritization of very important resources like forage quality could influence reproductive output compared to conspecifics if it ends up influencing fitness. And so variation in optimality could actually play a role in population dynamics. So I wanted to look at optimality, and I built an optimality clustering model. So I wanted to know how optimally are migrants timing their movements compared to peak forage quality. So I defined this metric of optimality here. And essentially what we're doing over our 3 periods here, pre, during, post-migration, per individual, is I'm taking each of the individual locations, the contemporaneous value the individual would actually be encountering at that time, and comparing that to the absolute maximum peak forage quality at that location for the year, and looking at the difference. So put succinctly, how close to perfect are they? And then I generated a cluster model to investigate optimality heterogeneity, see how much they're varying in an individual fashion. And here is kind of what the output of that model looks like, a static image of it. And I do want to explain the axes here, so it makes a little more sense. So this migration axis here is the corridor. The winter range is the pre-departure period. The summer range is that post-arrival period. Remember, that's 2 weeks on either side of the migration itself. And what we kind of want to look for here is if they're up here in this top right corner in association with these axes, they're exhibiting high optimality in all 3 periods. And so what we're seeing here are these kind of 2 individual clusters that are colored here, blue and red. The red cluster is a sort of suboptimal cluster. When is that being covered? Interesting, something's on the screen, that's fine. But the suboptimal cluster is in the red. You can see there's a tremendous amount of variation. They seem to be engaging in high levels of trade-offs because they're not up in that top right corner, whereas the blue clusters, this optimal cluster, are much more densely packed, and they seem to be more optimal on average. And so if we want to look at the distributions of these optimalities in a period-specific fashion per cluster, we can see that this blue cluster here is more highly optimal on average with respect to every single period than the red cluster. Whereas the red cluster, again, is showing this high level of variation. And something that's interesting to point out here is they seem to be more similar with respect to the post-arrival on average than they are with respect to optimality in the other 2 regions, which is pretty cool. And even though it's a clustering model, there's not a very clear, obvious delineation between the 2 of these. It should be interpreted much more like a gradient of optimality along all 3 of these axes. And kind of the takeaway here is there's very high variation, and this seems to infer that there are trade-offs among individuals. Imply, not infer, that's fine. I really want to show you guys this, but I think the hyperlink is going to break the PowerPoint. I have basically like a manipulable 3D version of this, so you can really get a feel for the variation. Maybe if people ask them the questions, we can try to pull that out, but we'll skip it for now. So another thing that was interesting about this is that the actual distribution in a study area specific fashion among clusters was not equal at all. Avalanche was basically half and half, suboptimal and optimal. Bears Ears was overwhelmingly optimal at 82%, whereas Uncompahgre was overwhelmingly suboptimal at about 70%. So their response to forage quality and optimality in that herd seems to be a lot less strong than any other herds. And so some takeaways from that chapter are that phenology and distances are actually variable among and within herds. And we have this really cool evidence for this kind of dual plastic modulation in both departure date and duration in response to peak forage quality in multiple sections of the migration itself. So elk appear to both surf and prioritize timing of arrival to reduce that phenological mismatch. And again, we have this gradient of optimality along differing periods of migratory events, and there seems to be a lot of heterogeneity among individuals. So just to get to some theoretical implications or conclusions, I found that resource response is largely context specific and inconsistent, but I did find evidence for varieties of differentiation and selection among strategies. Excuse me. So if differing responses could facilitate reductions in intra-specific competition, especially on overwinter ranges where strategies are sharing spaces, this is a possible mechanism for maintenance of partial migration. And if that's the case, then this can influence carrying capacity, basically effectively raising it because they're not competing for the same resources, and that could influence population densities positively. If that's the case, then this is a major benefit of partial migration mechanistically. I also found that elk migration is highly plastic and is influenced by resource phenology, both along migratory corridors and at the summer range, and that there seems to be a dual modulation of those parameters in order to optimize access in both cases to peak forage. And I found that not all migrants are created equally. Trade-offs are occurring in migratory movements. There's high inter-individual diversity, and this may confer differential access to quality forage, which could have fitness implications. Lastly, I want to talk about management implications. So if everything I just said is the case, then movement strategy diversity could offer population benefits, and in partially migratory populations, we want to aim to preserve that diversity. My resource model results can inform management of the most important resources within these populations, and it can do so in a strategy-specific fashion. I found overwhelmingly that anthropogenic development on elk winter ranges should negatively impact selection. So we want to be very thoughtful about the way we attain any development on their winter ranges. I found that corridors and summer ranges drive migratory phenology, so they are in special need of protection. I mapped corridors and seasonal ranges, and doing so it can inform future development so that we don't basically increase the fragmentation along these corridors and disrupt these migrations. And lastly, if there is a strong association between vegetative greenup and migratory phenology, climate change is very likely to alter greenup dates in the future, and so it may alter migratory phenology in very complex and unpredictable ways. I have a lot of acknowledgements and thanks. Primarily Colorado Parks and Wildlife, who collected and shared all of this data and provided the vast majority of the funding. The funding was also provided by SIU and the Klemstra Fellowship. And there are a number of organizations associated with elk conservation to thank: Rocky Mountain Elk Foundation, Vermejo Park Ranch, Virginia Wellington Cabot Foundation, the Bureau of Land Management, U.S. Forest Service, and Pitkin County. And of course, my advisors on my committee, Dr. Bastille-Rousseau, Dr. Vail, who came all the way from Colorado just to see this, Dr. Brown and Dr. Lovern, and of course the lab and all of the students in the SWEL and CWRL, and most importantly, my friends and family, without whom I surely would not have survived any of this. So if anyone has any questions, that is the end.